Okay, let's get started here. So assignment number 6 was graded since we last met. Were there by chance any questions? Okay. Today we will finish this control structures section and then start a new section on how to manage data properly in R. Are there any questions? Okay. So last time we were talking about Monte Carlo simulation, specifically with respect to trying to estimate the true confidence level for a confidence interval involving a population mean. And we were looking at a number of different ways to code the Monte Carlo simulation into R. All these ways so far have involved using a for loop. So the very first way, just as a reminder, this is on bottom page 7, top of page 8. We basically created a matrix to save our results in terms of all the confidence intervals that we're going to calculate during this Monte Carlo simulation, and also whether or not the interval actually contains the true value of mu, which was, I believe, 2. And so inside the for loop, we simulate our data, we calculate the lower bound, the upper bound of the interval, and then we do a check. Is mu inside the interval? And then lastly, we save the results. And if we take the mean of all these checked values, which are 1s if the interval contains mu, 0 if it does not. If we find the mean of all those values, we get 0.949, which means the estimated true confidence level is just about 95%. And this is what we would expect in this particular case, because alpha is 0.05. So then we were looking at other ways to do the same kind of coding. The first way was to actually simulate all the data up front before you go into the for loop. Sometimes you can't do that, depending upon how complex the data structure is. But when you can, it's often better in terms of more efficient and less time-consuming if you can do it up front. So we did that. If you remember, we put the result, all the data into a matrix so that each row was one simulated data set. And so there were 1,000 rows because we had 1,000 different data sets. Then we did a for loop again where we calculated the interval, this time just using one line of code. The key was that we were pulling out each of the data sets one at a time inside the for loop. Then we perform our check, we save the results, and again, we get the same estimated true confidence level. And so we ended up with the question, well, can we do better? And I said, yes, we can. So let's look at how we can. Okay, so again, I'm going to create a matrix that actually contains all my saved results. This time what I'm going to do is only make it have 2 columns, a column for the lower bound, a column for the upper bound for each of the intervals. Then with my for loop, using the for function, I say I in 1 to the number of samples, which would be 1,000. We have 1,000 different samples or 1,000 different data sets. I calculate the interval every single time, and the way that I do that is I pull out always the ith row corresponding to the ith data set. And then now I immediately put all the lower bounds and upper bounds immediately into my save.results matrix. I don't do the check inside the loop because that's not very efficient. Because now outside the loop, what I can do is take advantage of how R does its calculations using vectors. And in the first column of save.results3 is the lower bound. So I check all at once. The first lower bound, the second lower bound, and so on. I check, is it less than mu? Also, I do the same thing with the upper bound as well. And so what I get then is vectors of 1s and 0s. 1 if it's in the interval, 0 if it's not. And look at that. When I take the mean of all those check values, I get 0.949. This is much more efficient than what we have been doing. Any questions? Again, for this simplistic of an example, with this simple interval, the time considerations in terms of how long it would take to complete this, you're not going to see much of a difference. But in other situations I expect most of you will face later on during your academic careers, it will make a difference. The key is always try to take advantage of these vector calculations that R can do. Okay. Now, to my notes again. Let's look at a little bit of a different data structure. So far, all our simulated data sets were in one matrix. Every row was one simulated data set. Okay? Oftentimes, data that you use is not organized in that kind of manner. Let's say, for example, that you're doing some kind of Monte Carlo simulation with respect to regression, simple linear regression. Okay? In that case, you're always going to have an x, you're always going to have a y. And so if you imagine that this is our data frame, we have two columns, x and y, and maybe we have 10 observations per data set. So there's your first data set. It's structured like you would normally see a data set. You know, the x column contains 10 observations. The y column contains 10 observations. But in the Monte Carlo simulation setting, you have more than one data set. So now the next data set could be structured so it's right underneath that previous data set. And so that this is data set 1, this is data set 2, and you can keep on going down to data set 1,000. And that's how your data set's organized, so that now you have 10,000 rows. This is very common to see. Now the question is, well, if it's structured like that, what kind of modification do I need to make to my code? Okay. Well, when I was coming up with an example here, I thought, well, maybe I should just come up with a whole brand new Monte Carlo simulation setting, where we do have an x and we do have a y. I decided not to. Rather, what I decided to do was just simply restructure the data, that simulated data that we've been looking at, in essentially this form. In the end, we'll only have the y column, and so it's a little bit, just a little bit simpler, but the same concepts will apply to these more complex settings. Okay. So let me come over here. Oops. Oh, shoot. I don't know why 10 does this. So again, in case you didn't see what happened, in my office, I have multiple monitors. And I always keep 10 open in one of my external monitors, not this particular monitor here. And originally, when I opened up my program, it was in the window that you saw, but it wasn't minimized, it wasn't maximized, it wasn't taking up the whole window. So I decided to take the whole window up, and what did it do? It basically put it off into my external monitor, which I don't have plugged into my computer right now. So now I just closed 10, and then I want to reopen it, and you don't see it because it's in the external monitor. This is frustrating. Anybody using 10 by chance? Or is everyone using RStudio in this class? Trust me, 10 does have advantages. Okay, where the hell? Because I don't want to screw up the recording. That's my issue. Take the time before class to get everything open, ready to go, so we don't waste time during class. And look what happens. It's not a good day. The problem with RStudio that you can't just simply drag and drop a file in there to open it. It's difficult. There we go. Open. There we go, yay! It's been a frustrating day so far. Have you ever tried to get a flight to someplace and you see maybe it's like $400. And then you say, well, I'm going to wait a day, I'm going to buy it tomorrow. And then the price goes up to $550. That happened to me this morning. I'm going to a conference in March, and I thought, oh, I'm just going to start buying my ticket. I'm just going to get it over with. And Southwest had been telling me it was like $400 my flight to D.C. And I was going to buy it last night about 10 p.m., and then I realized that I didn't have the university's credit card number that I needed to use rather than using my own. So I couldn't buy it. So then first thing this morning, I go get the university credit card, or the departmental credit card, and I go to buy it, and now it's $550. And now it's like, well, maybe I don't want that flight. Okay, enough about that. Where were we? We were talking about this different data format. So I'm going to just simulate my data again, and the key is, see, this is what I don't like about using RStudio in class, because it's hard to see my program and the output window at exactly the same time. So I'm going to simulate my data again. In this time, the number of columns is just going to be 1. So that the first 10 rows will be the first data set, the next 10 rows will be the next data set, and so on. Is everyone clear? Any questions? Okay. Now, to do this then, I'm going to again save my results into a matrix. And for my for loop, the key to doing this, is to figure out an automated way to say I want rows 1 through 10 in my data set. Next time I want rows 11 through 20, and so on. You may have run into these kinds of issues before in other kinds of programming settings that you've encountered. And so this is how I do it here. I'm going to create an object called indices that basically gives me which row numbers to pull out of my data frame that has all my data sets. And so sample.size is 10. If I multiply that by I minus 1 and then add plus 1 to it, look what happens. The first time through the loop, I get 10 times 1 minus 1, which is 0, plus 1 is 1. So I have the first, I'm dealing with the first row. Then I want to go up to I times the sample size. So the first time through the loop, 1 times the sample size is 10. So my indices then become 1 to 10. The next time through the loop, I is equal to 2. Look what happens. I have a 2 minus 1 here, or 1. And I take that times the sample size of 10. I add 1 to it, and I get 11. Now over here, I is 2. 2 times the sample size is 10, you get 20. And so,
you moved it over. The I minus 1.
Thank you. So for example, so let's say I is greater than, or I gets 2. Here's a nice little like debugging tool that you can use just to make sure everything's working. And you get the right indices. Okay? So it's just a matter of making sure that you get that. Then, excuse me, to calculate my interval, I made a small change to the notes. The notes, they run fine. How I do is fine, okay? But I put a comma 1 there. Or let me just show you the notes because it's easier to see there. And also I put a comma 1 right here. So this is where I need to extract my data corresponding to the rows that I want. So this will give me rows, first time through the loop, rows 1 through 10, column 1. And the same thing is done over there when I do the standard deviation. Okay. Now as I say there, or what I said I should say, that this works as is. The reason being is because there's only one column to the data set. So because of that, you don't actually have to specify column 1. Okay? And in fact, this would work too if I only gave a comma there, which says take all the columns, there's just 1. That would work as well. Now, one of the reasons why I'm going through this, because this can be frustrating to some students I have found, understanding these small little concepts. Because trust me, I've run into a number of situations. Students bring it to me and say, I can't get this to run. Oh, okay. Now, when I do have more than one column, I do need to specify comma, let's say 1:2, or if I wanted the whole column, just a comma. Okay? So I calculate my interval. I put all the intervals in there, and everything will work just like before. You get 0.949. Okay. Any questions? Yes?
Since you do the same calculations, will I be able to do parallel computation?
Okay, that's a good question. So what you're interested in is, can more than one processor be used? With the for loop, no. But there are other functions that you can use to do parallel processing. If you want to see examples of that, you can take a look at my computational statistics notes when I talk about high performance computing, HPC. Okay? So the question, just to make sure you understand this, because this is an important thing that's changing how we do computations. In a very simple context, every computer nowadays it has a processor that has is multi-core or multiple cores. Does anybody understand? Without you telling me what the answer is, could someone tell me what a multi-core processor means? I mean, you see that out there a lot. Like for example, my wife just bought a new Amazon Fire Stick for our TV, and it's a 4-core. It has a 4-core processor in it. Anybody know what multi-core means? Okay. Imagine that this square represents your processor. Okay. Now inside your processor, you essentially have if it's a quad core, for example, it has 4 different, essentially different processors in it. So the way that R operates is that it will send, like if I run all this code, it will send it to 1 core. Let's actually back up here. This for loop here will send it to 1 core. Okay? But if you have 4 cores, and each of these cores can do the calculations completely on their own, you might be thinking, well, if I'm doing something 1,000 times, why couldn't this for loop essentially put 250 here, 250 here, 250 here, and I can't really write very well, 250 there. And so how long is this whole thing going to take? About 1/4 of the amount of time it would have took previously. And so the whole idea of using multiple cores there, take advantage of the full power of your computers, is called parallel processing. This is a simplistic case. We have supercomputers, for example, here on campus that will allow you to, well, easily access maybe, let's say, 64 cores at one time. And if you're really good, you could actually access hundreds or even thousands of cores at one time. And I personally believe that this is one thing. It's not just changing how computations are done elsewhere in many disciplines, but especially in statistics itself. That we could essentially rewrite a lot of our algorithms that we use to do computations so it can be done in a parallel context and greatly make things go faster. In this particular setting, this is Monte Carlo simulation, so this is what's often called an embarrassingly parallel setting. But there's many other settings that are not like that, where the cores actually have to communicate with one another to get stuff done. Where in this case, the cores can operate separately, get the job done, and come back together. This is more information than what you want, perhaps, but this is something I really think is cool, and I think this is an area that statisticians can get more involved in. If you want to know more about that, take a look at my computational statistics lecture notes. This corresponds to what is now called Stat 950. When I taught computational statistics in the past, it was Stat 992. They are online. High performance computing section. Okay. And so R actually, through certain additions that have been made to it, can actually do parallel processing. It's just not something I would teach in this class. Okay, let's talk about now debugging. When you first write this for loop, I wouldn't be surprised that it's not going to work the first time that you run it, because maybe you just forgot simple parentheses or something. And so oftentimes you're going to need to figure out what's going wrong. And one thing that I showed you already, a great technique that's used, is to simply, I have it here. I guess actually I did in our studio. It's to simply do something like this. Set I to a particular value, and then run it then for that one data set to see what happens. Another thing that you can do is to print stuff from inside the loop. So, for example, let's say that I just have this loop running for the first 3 data sets, because I'm trying to do some debugging. I don't need to see all 1,000. I'm just going to do the first 3. And inside my for loop, if you want to have something that's actually printed to your screen, you have 2 things that you can do. You can use the cap function. We saw that in the introduction to our lecture notes. It allows you to put just plain text that you type together with some of the actual object values. So, for example, I might want to print, well, what iteration am I at? So I say, quote, iteration, end quote, comma, I print I. And then I add some more information, where indices equal, and then I print the indices. Okay. Then also something that you can do is you can use a function print. So let's say I want to actually see what the interval is for every single iteration as it's going along. So I can say print interval. I cannot just simply say interval itself. So, previously when we've been at a command prompt, if you just type the object name, it's printed. Well, when you're inside a for loop, that doesn't work. You have to actually formally say print. So when I actually run this code, you can see iteration 1. Here's the indices. Here's the interval. And if something's going on wrong, let's say maybe you get maybe the for loop dies after 2 iterations. Then oh, okay, the problem's occurring somewhere between 2 and 3. And that could lead you then to figuring out what the solution is. These are simple programming techniques, and I wouldn't be surprised if most of you have done these kinds of techniques before. But again, what I've found through my experience is that not all students know about doing stuff like this. Okay, here's a useful alternative to using the for loop. We can use what's called the apply function. I never saw something like this in my other programming languages that I had experience with. I hadn't seen something like this before until I came to R. Maybe it exists in other programming languages, but I hadn't seen it yet. Now, the advantage, you can basically do the same thing with the for loop as you can with apply. The advantages of using apply is that the syntax itself is cleaner. Maybe it's easier to read once you gain experience with using apply. A second reason that some people have said in the past, which is not true anymore, but I do want to bring this up because when you do web searches, you'll still see people say this is a second reason. These people will say that apply is actually faster than for. And that's no longer the case. It used to be the case when people were still using S+. There was a problem with S+ that caused apply to be faster than for, but that's no longer the case with R. Okay, so let's talk about how we can use the apply function. Let's get back to the same format, or the original format of the data that we saw before, where every row was a data set. And so I want to basically essentially calculate the interval for every single row. So how about we just write a function that calculates the interval? So in the function itself, I'm going to pass in the data. We're just going to call it y for the lack of a better object name. I'm also going to pass in the value of alpha and also the sample size. And inside here, imagine that we're just doing it for one data set. I have my code to do the interval. I'm going to have a lower bound and an upper bound that's returned back to me. Now to basically now take advantage of this function, I can essentially apply this function to each row of my simulated data. So I'm going to say apply, and the first argument x is where my data is located. It's in y. And then I need to say, well, how do I want to apply it? Do I want to apply it by row or by column? By row corresponds to the margin equal 1 value. So margin is an argument. Margin equal 2 would be by column. I don't know why they just don't say row or column, but it's 1 or 2. And then what function do I want to apply to every row? And so I use the fun argument. I'm going to have some fun here and apply calc.interval to every single row. Now, what that's going to cause R to do is going to take a row from y and put it in the very first argument of this function. But you see that there's also some other arguments. So R allows you to then set values to these other arguments. So right after calc.interval, I have alpha and I have sample size. And it just so happens, I mean, it's the same name. You know, this is alpha here is the same name as alpha. It's just for convenience. So when I do this apply thing, go over here to RStudio. Save.results then is returned like this. Okay. I have 2 rows, 1,000 columns. Each column is a result from calc.interval. So the last data set 1,000, has an interval of negative 1.46 to 4.69. And again, I can check to see if mu is in the interval, and I get 0.949 once again. I want to also take a look at the help for apply. Okay. Under usage, notice X argument, margin argument, fun argument. Then we have these ... dots. Have you seen these ... dots before? They exist with some functions. What these ... dots allow you to do is to pass in additional arguments that might be used, for example, like by a function that needs them. So if we look back at my code here, we do some erasing. We see that I have these 2 additional arguments. This function will not run without values for those additional arguments. And so I need a way to somehow say, well, what are those additional argument values are? And since I have that ... part there that you saw for apply allows me to put in these additional arguments. And when they're needed, they will be used. A very important concept to understand, more of an advanced concept to understand when one is using R. Very useful it can be. Any questions? Yes?
So can we use any function within, like any function that we wrote?
Yep, you can use any function you wrote or has already been written. So for example, let's take a look at another use of apply. Here's another way that we can find that estimated true confidence level. How about, first of all, I take advantage of a function called row means, and I find the mean of every single row in Y. Okay? So Y bar is going to have 1,000 different means in it. Next, I'm going to use the apply function once again. Apply it to Y by row. What function do I want to apply? How about the standard deviation? I don't need any additional arguments with that. So SD.Y is going to contain 1,000 standard deviations. And now once again, I can take advantage of how R does its calculations using vectors to find the lower bound of the interval. Here's 1,000 Y bars plus that the lower value, that negative value from the t distribution, times 1,000 standard deviations divided by the square root of 10. I do the same thing for the upper bound, but I change which quantile to get from the t distribution. I apply check, and look at this. I get exactly the same thing. And for this kind of a simple setting, this is probably the most efficient way to do this, to do these calculations. So, questions. Rather than using row means, how would you use the apply function to find the mean of every column? I'm sorry, of every row. What would you do? Apply, x equal y, margin equal 1, fun equal what? Mean. Okay, I could have done that instead. Question 2. Why do you think the interval needed to be calculated in 2 lines of code rather than 1 line of code that, like I had been done previously? Why did I calculate the lower limit separately from the upper limit when we had seen cases where, like with the calc.interval function, I calculated both of them exactly the same time? Here's calc.interval. So the key way that I was able to do the calculation here, I had 1 mean plus 2 t-distribution values times 1 standard deviation divided by 1 sample size. Now look what would happen if you translated that into what we are doing here. I have 1,000 means, and if I would have put those 2 probabilities in there, I would have had 2 values from the t-distribution times 1,000 standard deviations divided by the square root of the sample size. R wouldn't know how to handle this. This is where you can get into trouble then doing these vector calculations. That you have a vector of size 1,000, but you also have a vector of size 2. How do we do that? And so that's why I needed to do it separately. Try it on your own, not separately, and see what happens. So there are many other actually applied functions out there. In particular, there's like the lapply function. So if you're working with lists, you can apply certain functions to each component of a list, lapply. There's also other looping structures out there, but they're rarely used. Typically, only the for function is used. Okay. Any questions? Let's move on. Next section. Okay, summarizing and managing data. Sometimes the hardest part of data analysis is to get the data into the correct form. So what we're going to talk about here are some techniques that one can use to get the data into a desired form that one can use to apply with a particular function. We took some time to do this, for example, in the SAS section as well. Sometimes this isn't the most interesting things to do in the world, but it's extremely important, and you can get very frustrated by not having the data in the correct form. Okay, so far we talked about like how to add variables to a data set. So let's say I have a data set that's called set 1. So set 1 is a data frame. Oops. Let's get my red pen out. There's my colors. There we go. And maybe you have a data frame called set 1, and you wanted to add a variable to it. So you have set 1, comma, whatever that other variable is, and that's how you can add a variable to the data frame. Another way to do that is to say, okay, here's my set 1. I'm going to create this new variable in it, so it gets then whatever values I have over there. You can also create new variables by using the if-else function, as we've seen. And then there's some other ways that are helpful for combining data frames and stuff like this. We have not talked about, I don't think, R-bind. Have we talked about R-bind or C-bind yet? I don't think we have. Okay. Originally, when I had constructed these notes, I was going to do the matrix algebra section before this one, and that's where we would talk about those functions. And so I'll talk about them as needed when we go along here. And have we talked about recycling before? Okay. We will talk about recycling later. So let's look at some simple examples. Let's say I have 2 data frames, set 1 and set 2, and I want to merge them together. So a common setting that people often face is, let's say if you have two data sets, and they each row has a person's name in it. And what you would like to be able to do is somehow merge this data set here with this data set here by name, so that you can have the other stuff that might be in the data set shared and put together. So this is a simplistic example of how you could do that. So let's say these data frames have a name 1 and a name 2 column. Rather than actually typing out names, I just typed A, B, and C because it was easier. And here we have like some kind of response associated with each individual as well. So those are what the data frames are. And to merge them together, as you might expect, there's a function called merge. So I'm going to merge set 1 with set 2. And then what some people might call in maybe in a computer science setting, they might say, well, what's the key the key variable or the key field that you're using to merge stuff together? Well, I'm going to merge in my X data set by name 1, my Y data set by name 2, all equal true. That says, hey, if there's something that's in X but not in Y, we'll still keep it in the data frame. If all equals false, if all equals false, it would actually remove it. So here we go. In the data frame itself, we can see that there's one A here, and there's two A's in set 2. A response of 10 and 11 in set 2. In set 1, a response of 1. Look at how R reacted here. It duplicated that 1, and then you also have the 10 and the 11. Also, there was somebody with the name of F in set 1. In set 2, there wasn't an F. Look what happened here. Response 1 of 6, response 2 of NA, because there wasn't a value for in set 2 for F. Now, when we do the all equal false, look what happens. You do not see F appear. So, that's the merge function. Another useful function is called expand.grid. This is useful in settings where, let's say you have two variables, and you need to figure out all possible combinations of these two variables, and you want to put them in a data frame. So in a very simplistic setting, let's say X is 1, 2, and 3. Y is either A or B. And when I say expand.grid, X comma Y, look what happens. We get all pairwise combinations. I use expand.grid. I would say frequently, but I have used it many times. Notice what's first and what's second. The first variable is what varies the most. That's often the terminology that people use. So you see the 1, 2, 3s are varying, not varying the most, varying the fastest. So those values are changing the fastest. The value in the second entry here is changing the slowest. So you have A, and B, B. And if I were to flip-flop the Y and the X, you can see how now the A's are varying the fastest. What about sorting? Well, it's not as easy as it is in sets. Well, I wouldn't say it's difficult. It's just there's not like a proc sort. Well, there is a sort function. So let's say, for example, I have X. It has values of B, C, and 1. And I want to sort it. So, as you might expect, I use a function called sort. And I get 1, B, C. Okay? That makes sense. B comes before C. Numbers are typically thought of as coming before letters whenever you do any kind of sorting in a computer setting. If I had a capital B there, that would go after the lowercase b. So lowercase first, uppercase second. But let's say I have a data frame that looks like this, where I have an ID variable. So again, very common in a data set form, where you have some kind of thing that's going to identify every single row uniquely. And then we have some kind of response associated with that. If these are people, response associated with that person. And you might think, okay, let's just use sort. Ooh, doesn't work. This is what makes it a little bit different from what maybe you're used to. Instead, what you need to do is use the order function. Okay. So when I say order set1 $ID, look what happens. This 2 here says row 2 has the smallest value. This 3 here says that row 3 has the next smallest value, and so on. And remember how we can combine basically numbers like that as the row indices of a data frame. And so when I do that, so when I put order then as the row indices for set 1, that's how I get everything sorted. Because this tells R, I want to see row 2 first, I want to see row 3 next, and then row 1 last. That's how you do sorting in R. It's the order function. Let's look at another example. So now in this case, I have 3 variables. I have an ID, I have a response 1, and a response 2. And if I say, well, let's again sort by ID, as you might expect, what's going to happen. Let me actually open this up in here. Okay, so make that bigger. So this order for the ID, notice I have a 2, 2, and a 1. So what comes first? Row 3, because it has the smallest value. Then what comes next? Well, I have a tie. I have a 2 and a 2, and so R just simply leaves it in the same order as it was before. 1 and then a 2. Okay, so that's how I got this sorted here. But let's say I want to sort by more than one variable. Let's say I want to sort by ID and then also response 1. Look at response 1 right here. Okay? Notice how the 10 is smaller than the 20. So you're going to see that flip. So when I put both those in order, look what happens then. I have those observations flip. So that's how you can sort by more than one variable. Now, one thing that you'll notice here, in all these data frames, I have, and we've seen this before, row names. And it makes sense for that first data frame up here. I have, row name 1, row name 2, row name 3. But after you sort, look what happens. You have the original row name still there. And to some respect, I find that kind of annoying. So what can you do? One thing that you can do, I think you saw this in a assignment, is you can say print, if set 2 contains my sorted data, I can say print set 2, comma, row dot names equal false. And then you will no longer have any kind of row names. But maybe you still might want to have row names or I'm sorry, excuse me, maybe you just simply, because it can be useful to see essentially the observation number there. So what can you do? Well, you can use row.names. That's actually a function. Parentheses, if your data is in set 2, gets a value of null. Null means nothing. And notice when I do that, I don't actually get nothing. I get just simply the numerical order again. But this is one thing that's interesting about this. Row.names is one of the few R functions that you can actually use on the left side of an assignment. So notice, well, everything that we've done before, whenever we use a function, we always put it on the right side of an assignment. Row.names is one of the few functions that you can actually put on the left side of an assignment. Kind of weird. Okay. So, I think that's a good place to stop. Are there any questions? Okay, then that's it for today.